Hello friends, in this video we will be seeing class 12 chapter number 1 relation and function. So in this video we will be seeing all the concepts and the examples which are required to solve exercise 1.1. So as we know, in daily life we have a relation in our houses. So you have a relation like father, mother, son, daughter are the relations within our houses. The same way, if you have two different houses, then you have a relationship like uncle, aunt, cousin, and all. The same way, even in the max also, we have a relation between two objects. So first we will take an example and we'll explain. So consider if we have an two set, that is A is 1, 2 and 3, and one more set is 4, 5 and 6. So these two are objects, that is set A is having 1 and 2, 3 and set B has 4, 5 and 6. So here the set A has a relationship with B, like 1 has a relation with 4, 5 and 6, and when 2 can have a relationship with 4, 5, 6 and 3 also can have a relationship with 4, 5 and 6. So first we have to write a Cartesian product. So how do we write a Cartesian product? So first is the Cartesian product that will denote it as A into B. So we are going to write A cross B, that is nothing but 1 comma 4, 1 comma 5, 1 comma 6, then 2 comma 4, 2 comma 5, 2 comma 6, then 3 comma 4, 3 comma 5, 3 comma 6. So these are the ordered pairs we get when we do A cross B. So usually in our ordered pairs, the first element will be from set A and the second element will be from the set B. Totally 9 ordered pairs for A cross B. Few will ask, why can't we write B cross A? Of course, we can write B cross A, but here the relation will be from B to A. So here we have to take this as a first set and this A as a second set. So the way we write is 4 comma 1, 4 comma 2, 4 comma 3, 5 comma 1, 5 comma 2, 5 comma 3, 6 comma 1, 6 comma 2, 6 comma 3. But you can see the first element belongs to set B, sorry, first element belongs to set B and the second element belongs to set A. And you can see A cross B and B cross A is not same. So the first element of A cross B is from A and second element is from B. The same way B cross A, the first element is from B and the second element is from A. They are not same. So we have totally here 9 ordered pairs. If you have another set like A has something 100 and B has some 50, then how many order pairs can you write? You can't keep on writing. So how many order pairs are there? To know that, you have to multiply. Imagine you have some, that is nothing but m into n. So here we have 3 cross 3, we got it as 9 ordered pairs. The same way here we have 100 into 50 is equal to 5000 ordered pairs. Now let's see what is relation. So we'll take the same example A cross B. So A cross B, and we are taking an relation R. R is equal to, so 1, 4, 2, 5 and 3, 6. So it will be 1 comma 4, 2 comma 5 and 3 comma 6. So this is an relation, and we'll tell that always the relation is nothing but a link or a connection. So it is a link or a connection between two objects. So here they have given us a roster method. Roster form. Okay, so here they have given us a roster form that is nothing but 1 comma 4, 2 comma 5 and 3 comma 6 is in relation. Okay, so in how they are related, how 1 is related to 4, how 2 is related to 4, we'll write it in a set builder form. Builder form, that is nothing but, so A comma B belongs to A cross B, that is B minus A is equal to 3. So here the relation tells that A comma B belongs to A cross B only if B minus A is 3. So here we have taken these three elements, that is 4 minus 1 is 3, again 5 minus 2 is 3, 6 minus 3 is 3. So this is my relation. So if you want, we can write it in another method called, we'll write 2, 3 belongs to set A and B 4, 5 and 6. So 6. So this is called mapping. So here 1 is related to 4, 2 is related to 5, 3 is related to 6. The relation is always a subset of A cross B. So whatever, this is nothing but a subset of A cross B, because this has totally 9 elements, in that only the 4 elements we have taken. So it is a subset of A cross B. Then we have to find out how many number of subsets you get like this. For that we have a formula, is that is nothing but 2 to the power of m into n. Here I have 3 elements of A and 3 elements of B. So totally we'll have 2 to the power of 3 into 3, that is 2 to the power of 9 subsets we'll obtain from A cross B. In this chapter, we will be doing the problems with the same set, like set A is 1, 2, 3. Then we are going to find the relation for the same set, empty relation. So here the relation will not have any element, means the relation has no elements, that is R is equal to null. So relation does not have any elements, that is null, or you can represent it as within the flower basis no elements. So for example, if you take the previous example, R is equal to A comma B is a subset, or is a, so R is equal to A comma B belongs to A cross B, that is if A plus B is equal to 10, so is equal to 10, obviously because A is nothing but 1, 2 and 3 and B is 4, 5 and 6. So here if you add 3 plus 6 you get 9, but you does not get 10. So none of the element, if you add any elements you will not get 10. So R is nothing but a null. You does not have any ordered pair. So that relation we called it as empty set. The next is the universal set. The universal relation. So the relation will have all the ordered pairs of A cross B. So relation has all the elements. That is, relation will have all, it belongs to all the A cross B. Means all the ordered pairs of A cross B is called universal set. Next is reflexive. So relation is said to be reflexive if A comma A belongs to R for every A cross A. So here all the elements means a comma a should belongs to R for every a comma b. So if we take an example as a is equal to 1 comma 2 comma 3. So we'll have a cross a is nothing but we'll have 1 comma 1, 1 comma 2, 2 comma 3 and 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2, 3 comma 3. So in this we take a relation is equal to nothing but 1 comma 1, 2 comma 2 and 3 comma 3. So here they have told that all the elements, A has how many elements? 1, 2, 3. So for 1, 2, 3 belongs to A, that is 1, 2 and 3 belongs to A. So it belongs to A and we should have 1 comma 1. So we should have 1 comma 1, 2 comma 2, 3 comma 3. These are mirror images. So you should have all the mirror images for all the elements of set A. So then only we call it as a reflexive. Symmetric. So in symmetric relation, we have to see if A and B belongs to R, A comma B belongs to R, then B comma A also should belongs to R. So if we are taking an example that 1 comma 1 and 1 comma 2, then 2 comma 1. So here if I am taking 1 comma 2 has an element, that is 1 comma 2 is belonging to R, then this implements that 2 comma 1 also should belongs to R. So here we are taking 1 comma 2. So 1 comma 2 belongs to R. Obviously it is there. Again that means that 2 comma 1. So we have 2 comma 1 also. Then we call it as a symmetric. Transitive. So transitive is nothing but if A comma B belongs to R, then B comma C belongs to R, then that means that A comma C should also belong to R. For an example, if we take 1 comma 1, 1 comma 2 and 2 comma 3. So we are taking and relation is nothing but we have a small example that is 1 comma 1, 1 comma 2 and 2 comma 3 and 1 comma 3 we have. So if we are taking 1 comma 1, so 1 comma 2 belongs to R. We have 1 comma 2 belongs to R. Then other one is this element that is 2 comma 3. So 2 comma 3 should also belongs to R. Here the second element and the first element of this ordered pair are same. So this means that you should have 1 comma 3 also in the relation. So even 1 comma 3 should also belong in the relation. So we have here 1 comma 3. So this is called a transitive. Equivalence relation. If relation satisfies reflexive, symmetric and transitive, then that relation is called equivalence relation. Example number 1. So here they've given, let A be the set of all the students of a boys school and show that the relation R in an A given by R is A comma B, that is A is a sister of B and is the empty relation, and A dash is equal to A comma B. The difference between the height of A and B is less than 3 meters is a universal relation. So here in this question they have given that there is a set A which has all the students of boys school. So it is a school of a boys. Then we have to show that the relation R in A. So we have a relation R in A such that A comma B and A is a sister of B. So first we will take for relation A. So for relation R. So as we know they have given that the relation is given that A is A comma B such that A is a sister of B. So we know that here the school. So here the school is of boys. So there is no girls in the school. So this is a boys school, so there is no girl students. So obviously when there is no girl students, there cannot be a sister of any student. So if there is a girl only, then there can be a sister of any student. So here there is no set, no element at all. So this relation is nothing but a empty relation, that is a null. That is R is a empty relation. So for next is A R dash. R dash is A comma B, that difference between the height of A and B is less than 3 meters. So for relation R dash, so they have given that R dash is A comma B, that is the difference between the height of A and B is less than 3 meters. The difference between the height of two students. So they have told that difference between the height of two students should be less than 3 meters. That is 9.8. Obviously, usually the man height will be max to the 6 feet. 6 feet. But here they have mentioned that it should be less than 3 meters. That is 9.8 foot. So obviously every student's, the difference between the height will be less than 3 meters only. So all the students will include in this. So it is a R dash is a universal relation. So all the boys will be there in this relation. So this is a universal relation. The second example, let T be the set of all the triangles in a plane with R a relation in T given by R is T1, T2, that is T1 is congruent to T2. Show that the R is an equivalence relation. So here they have given us a relation telling that T1, T2 is congruent. So they have told T1 is congruent to T2. So that is what is the relation R is given as T1, T2. That is T1 is congruent to T2. So we have to find out we have to tell this relation is an equivalence relation. So to find out equivalence relation, we have to satisfy 3 conditions, that is a reflexive, symmetric and transitive. The reflexive relation. All the triangles are congruent to itself. So we know that every triangle is congruent to itself. So if you take an triangle has A, B and C, so this triangle is congruent to itself. So all triangle will be congruent to itself. So obviously triangle T will be congruent to triangle T. Therefore T, T also belongs to R. So R is a reflexive. The next we have to check for a symmetric. So here if triangle 1 is congruent to triangle 2, then triangle 2 is also congruent to triangle 1. So we have this is a triangle 1 and this is triangle 2. So if triangle 1 is congruent to triangle 2, then obviously the triangle 2 will be also congruent to triangle 1. So T1, T2 belongs to R, then T2, T1 also belongs to R. Hence, R is a symmetry. So the relation R is also symmetric. So relation R is proved as symmetric because T1 is congruent to T2. Obviously T2 is also congruent to T1. So now we have to check for the transitive. So check transitive. So here if T1 is congruent, as we know that T1 is congruent to T2 and T2 is congruent to T3, then T1 is congruent to T3. So we know that if we take as T1 is a triangle is congruent to T2, then T2 is congruent to T3. So T1 is congruent. So T1 is congruent to T2 and T2 is congruent to T3. Then this is a common. So obviously T1 will be congruent to T2. So we can write this as, so T1 and T2, this belongs to R, and even T2, T3 belongs to R. Then obviously T1, T2 belongs to R. So R is a transitive. R is a transitive. So we have satisfied, the relationship has satisfied reflexive, symmetric and transitive. So R is a reflexive, symmetric and transitive. So therefore R is a equivalence relation. So we have proved that R is an equivalence relation because it has satisfied reflexive, symmetric and transitive. So it is called an equivalence relation. Example 3. Let L be the set of all lines in a plane and R be the relation in L defined as R is equal to L1, L2, where that is L1 is perpendicular to L2. Show that R is a symmetric but neither reflexive nor transitive. So they have given us L is a lines in all the planes. So all the lines are in the planes. So R be the relationship. So R is a relationship in L, defining that they have told that relation R, L1 and L2 such that L1 is perpendicular to L2. So line L1 is perpendicular to L2. So we have to check that that R is a symmetric but neither reflexive nor transitive. First we have to check for reflexive. So if R is a reflexive, so we know the condition, if R is reflexive, then line L1 and L1 should belongs to R. So here the line, if I write a line, this is my line. So this is line L. If I take a line and this I call it as L, so the same line should be perpendicular to itself. It is not possible. Always the line is parallel to it. It is not perpendicular. So line L cannot be perpendicular to itself. So line L cannot be perpendicular to the line itself. So L comma L will not belong to R because it's not a perpendicular. So therefore R is not a reflexive. Check for symmetric. If line L1 is perpendicular to L2, so we consider this has line 1 and this has line 2. So this is my L1 and this is my L2. So L1 is obviously perpendicular to L2. So line 1 is perpendicular to L2. Then line 2 is also perpendicular to L2. So that L1 comma L2 belongs to R. The same way we'll have L2 comma L1 also belongs to R. Therefore R is a symmetric. R is a symmetric. Now we have to check for the transitive. So if L1 is perpendicular to L3, now we'll consider this as, see, this is line L1 and this is my line L2. Okay, so line L1 is perpendicular to L. So we'll consider this is line 1 and line 2. So line 1 is perpendicular to L2. So that is there. Line 1 is perpendicular to line 2. Now we have line 2 is perpendicular. So for this, if I write one more perpendicular, this has a line 3. So line 2 is perpendicular to line 3. But line 1 is not line 1 L1 is not perpendicular to L3 because it is parallel. It cannot be perpendicular. So L1 is not perpendicular to L3. So it is not perpendicular to L3. So it is parallel to L3. So it is parallel to L3. So if L1, L2 belongs to R, then L2, L3 belongs to R, then L1, L3 does not belongs to R. R is not a transitive. Hence, we have proved that R is not a reflexive, it is a symmetric, and it's not a transitive. Fourth, show the relation R is the set 1, 2, 3 and given by a relation is 1, 1, 2, 2, 3, 3, 1, 2, 2, 3 is a reflexive but neither symmetric nor transitive. So they have given us a relation that is R is equal to 1, 1, 2, 2 and 3, 3, 1, 2 and 2, 3. So they have given us a relation that is 1, 1, 2, 2, then 3, 3, 1, 2 and 2, 3. So we have to check for the reflexive. So first is we will check for the reflexive. So we know that if a relation is said to be a reflexive, then we should have for A, A belongs to R for every A belongs to 1, 2, 3. So my A has 1, 2, 3. Then for every A 1, 2, 3, I should have A, A. So since we have 1, 1, 2, 2 and 3, 3. So we have 1 means we should have 1, 1, 2, 2, 2. For 3 we should have 3, 3. So since we have 1, 1, 2, 2 and 3, 3 belongs to R. So R is a reflexive. So it is proved that it is a reflexive. Next we have to check for symmetric. So we have to check for symmetric. So to check a symmetric, what is the condition is A should belongs to R, AB belongs to R, then BA also should belongs to R. So here we are going to take 1, 2. So hence here 1, 2 is belonging to R, but 2, 1 does not belongs to R. So here we have 1, 2 belongs to R. We have 1, 2, but 2, 1 is not there in the R. So therefore R is not symmetric. Next we have to check for transitive. So according to transitive, what it is, A, B should belongs to R and B, C should belongs to R, then A, C should belongs to R. This is the condition, right? So if here we take 1, 2 and 2, 3. So 1, 2 here 1 comma 2 belongs to R and 2 comma 3 belongs to R. But here 1 comma 2 is there, 2 comma 3 is there, but I should have 1 comma 3, where 1 comma 3 does not belongs to R. We does not have 1 comma 3 in the relation. So therefore R is not a transitive. So here the relation therefore R is reflexive but neither symmetric nor a transitive. So hence it is proved. So it is proved that it is reflexive, it's not symmetric, not transitive. So example number 5th. Show that the relation R is in the set Z of integers given that by R is equal to A comma B, that is 2 divides A minus B, is an equivalence relation. So here they have given us a relation where R is A comma B such that 2 is divides A minus B. So they have told that A minus B divided by 2 you should get as an integer. We'll first check for the reflexive. So since for according to the reflexive, where A comma A belongs to R for every A belongs to Z. So for every A belongs to Z means for every A in integer, so A comma A should belongs to R. So since we know that A minus B means we have to take that A minus A is 0. We know that A minus A is 0. So 2 divides 0. So 2 divides 0. Obviously, like 2 divides 0 is 0. Is an integer only. So therefore, that implements that 2 divides A minus A. So therefore, A comma A belongs to R. So therefore, R is a reflexive. So R is a reflexive because A minus of A itself is 0. So this 0 divided by 2 is obviously 0. So any number you take for A, again you will get a 0. It will be divided by 0. 0 is also an integer. Now we are going to check for symmetric. So symmetric. So if 2 divides A minus B, then 2 divides minus of minus AB. So that is nothing but B minus A. So I can write B minus A as minus of A minus B. So here it is again an integer only. So it is not nothing else. It is again an integer. So hence if A comma B belongs to R and then B comma A also belongs to R. So therefore R is a symmetric. So R is a symmetric. Next we will check for the transitive. So we know that transitive is AB belongs to R, then BC belongs to R. That implements that AC should belongs to R. So here if 2 divides AB and 2 divides b minus c. So 2 divides a minus b plus of b minus c. So also 2 divides a minus c. If 2 divides a minus b and 2 divides b minus c, so 2 divides, we can write this a minus c as a minus b plus of b minus c. So b and b get cancelled, we get a minus c. So 2 divides with a minus c also. For a roughly, we'll take an example. If 2 is dividing the 8 and again 2 is dividing the 12, so obviously 2 will divide 8 plus 12. So that is 20. You can write this. So if 2 is dividing 8 and 2 is dividing 12, then 2 can divide 8 plus 12, that is 20. Therefore, therefore R is transitive. So it has satisfied the reflexive, asymmetric and transitive. So our relation R is a equivalence relation. So we have proved that the relation R is an equivalence relation because it satisfies the reflexive, symmetric and transitive conditions. So example number 6, let R be the relation defined in a set A 1, 2, 3, 4, 5, 6 and 7 by relation R is A, B. Both A and B are either odd or even. Show that R is an equivalence relation. Further, show that all the elements of set 1, 3, 5 and 7 are related to each other and all the elements of subset 2, 4, 6 are related to each other, but no element of subset 1, 3, 5, 7 is related to any element of the subset 2, 4 and 6. So they have given us a set which has 1, 2, 3, 4, 5, 6 and 7 and they have given us a relation telling that both A and B is either odd or even. So we have a relation as A, B where both, that is the both A and B are either odd or even. So this is our relation. So A and B can be either odd or an even. So we have to check that it is an equivalence relation. So first, for equivalence relation, we have to check reflexive, symmetric and transitive. So first we will check for reflexive. Since we know A and A are the same numbers. So we know A and A is the same number. So both A and A must be either negative or the odd. So therefore A, A will always belongs to R. So R is a reflexive. So it is proved that R is a reflexive. We have to check for symmetric. So in symmetric, we know that A, B should belongs to R and B, A also should belongs to R. A and B is either odd or even, then B and A is also will be either odd or even. So if you take A is something 2 and B is 4, then it is even. So again 4 and 2 if you take, it is again an even. For an example, if A, B belongs to R and then B, A also belongs to R. Because if you take 1 and 3 and 1 is also an odd, both are odd. So R is a symmetric. So next we have to check for the transitive. So if both A and B are either odd even, so we know that A and B can be either odd or even, and when B and C can be either odd or even. So if A, B, C are either odd or even, then obviously A comma B will be either odd or the even. So A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R. So it is transitive, it is proved. So here we have proved it is reflexive, it is symmetric and transitive. So all three relations are being proved. So this is an equivalence relation. R is a reflexive, symmetric and transitive. So it is R is an equivalence relation. So we have proved that it is an equivalence relation. Now we have to show that the element of subset 1, 3, 5, 7, 1, 3, 5 and 7 are related to each other. So we have to show how 1, 3, 5 are related to each other, and the element of subset 2, 4 and 6 how they are related to each other, and no element of subset means odd is how odd is related to each other and how even are related to each other. Then we have to show that no element of odd is related to even. So we 1, 3, 5 and 7. So all the elements are here are the odd. So they are odd elements. So all elements are odd. So all elements are related to each other because all are odd. So 1 is odd, 3 is odd, 5 is odd, 7 is odd. Hence the elements of 1, 2, 3 are related to each other. Now so 2, 4 and 6. So here all the elements are even. So all the elements are here even. The elements of 2, 4, 6 are related to each other. Now we have to see that in 1, 3, 5 and 7 and 2 and 4 how they are not related. We have to check. Here 1 and 2, here 1, 2, 1, 3, 5 and 7 are odd, and 2, 4, 6 are even. So both the elements, if you are taking one element from odd and one element from even, so both element cannot be either odd or even. So if you are taking 1 and 2, so both cannot be odd or both cannot be even because one is odd and one is even. So we cannot relate each other. So 1, 3, 5 and 7 and 2, 4 and 6 are not related to each